The physics of ping pong. Before we start the analysis, Justin and I wanted to pose some questions. These questions were how to create top and backspin, what are the effects on the ball, and what physics elements could we incorporate in this project. So Justin, how do we create different types of spin for ping pong?
To create topspin, when the ball's coming at you, you want to hit the ball at an upward angle going off the side of it, which creates the ball to spin downward. For backspin, you actually want to do the complete opposite. When it's bouncing at you, you want to hit the ball at a downward motion, so the ball will spin backwards.
Here's an example of hitting topspin. Here's an example of backspin. So Justin, what are the effects of spin in ping pong?
For top spin, when the ball's spinning forward, the air is moving past it and a low air pressure zone is created below it, causing the ball to spin faster downward. For backspin, it's the complete opposite. When the ball's spinning backwards, the air, however, is going in the same way as the spin. Low pressure zone is created on top of the ball, causing the ball to slow down or to move backwards.
Here's a picture diagram of topspin and the effects of the ball. Here's a diagram of backspin and the effects of the ball.
The physics that we wanted to incorporate was the amount of force the paddle used to hit the ball, the amount of work used, the impulse the ball experiences, and the amount of torque on the ball.
Now to answer the questions that we proposed, we decided to put them to test. This next video shows our first attempt at topspin in slow motion.
As you can see here, as Travis hits the ball at an upward angle, the ball starts spinning downward and travels faster.
From this angle, you can see the ball spin and curve downwards. Here shows our first attempt at backspin in slow motion.
As Travis hits the ball at a downward angle, the ball spins backwards and tends to slow down.
From this angle, you can see how the ball better reacts to the spin as it slows down and floats upward.
Tracker is a software we use to help us with our calculations. In this video, we were capable of tracking the movement of the ping pong ball and the paddle. These position increments were recorded into data graphs that gave us the information needed for our equations. Some of the graphs we used were x component position, x component velocity, and x component momentum. Impulse is defined as the change of momentum. The formula that better represents this is final momentum minus initial momentum, or by the formula of force multiplied by time. We took the final momentum represented in this graph, which is 2.28, and subtracted it from the initial momentum of 0.35. So 2.28 minus 0.35 equals 1.93, and that was our impulse. Force is defined as the capacity to do work or cause physical change. The equation used to find force is mass multiplied by acceleration, or the equation we used of force equals impulse divided by time. We found our impulse, which is 1.93, and we found our seconds, which is 0.0048. We divided the two, so 1.93 divided by 0.0048 ended up equaling 405.3 newtons, and that was our force. Work is defined as when a force causes displacement. The equation that represents this is force multiplied by displacement. The way we found our displacement is we took our final displacement of negative 1.72 meters and we subtracted it from our initial, which was negative 1.73, which equaled out to 0.01 meters. And then to find work, we multiplied our force, which we found earlier, which was 405.3 newtons, and multiplied it by 0.01 meters. And that equaled out to 4.053 joules, which was our work. Torque is defined as a twisting force that causes rotation. The equation we used was radius of the object multiplied by force. Force that we found earlier was 405.3 newtons, and the radius of the ping pong we measured equaled out to 0.02 meters. So we multiplied 405.3 multiplied by 0.02 meters equaled 8.106 with Newton meters as our unit. And that was our torque.